Hello, my name is Callum and welcome to our in-depth video series on data pipelines. In my previous video, I covered what are APIs, a foundation for modern data pipelines. While we have been building data pipelines for a very long time, what has changed is the modern enabling technologies such as REST APIs and the advent of cloud and the ease of deploying code in a serverless environment. In my last video, I showed you how to create a simple API using API Gateway from AWS connected to a AWS Lambda function I wrote in Python and a simple JSON payload for a healthcare referral. In this video, I will go deeper into communication and transport mechanisms of the REST API. Following that, my focus will shift into data processing, where I will show you how data is mapped, extracted, and stored in systems. I will use a healthcare example and will be covering a global standard for data exchange called FHIR for the purpose for our demonstration. Let's explore how data pipelines facilitate these needs. Our case study revolves around a typical data pipeline architecture used by general practitioners or GPs. This involves integrating the practice management system software with secure electronic transmission systems. Without manual intervention, these pipelines ensure that referrals are sent directly from the GP system to the referral organization, such as a hospital or a specialist office. Security is paramount. The data pipelines include multiple layers of security protocols to protect sensitive patient data. This includes encryption, secure access control, and compliance with health data regulations, ensuring that every piece of data shared through the data pipeline maintains its integrity and confidentiality. By using these electronic referral systems, healthcare providers benefit from reduced paperwork, minimized errors, and faster processing times. This not only enhances the efficiency of the healthcare delivery, but also improves patients' experience by ensuring they receive the right care at the right time. Let's break down some key parts of setting up data pipelines, especially for sending electronic referrals in healthcare. First, communications and transport mechanisms. We use REST APIs to manage data transfers between systems. This is like using the internet to send and receive data packages efficiently. REST APIs operate with standard HTTP methods. This approach works well with cloud platforms like AWS, where APIs integrate seamlessly with other services. Next, security. Security is all about keeping data safe and ensuring it comes from and goes to the right place. We use techniques like digital certificates to verify the identity of the communicating parties. Think of these certificates like a digital passport that proves the legitimacy of the data's sender and receiver. Next, privacy and data sharing. Privacy involves making sure the data shared is handled accordingly to strict guidelines. This includes adhering to laws and regulations that protect personal information. Next, data exchange formats. Data needs to be in a format that both the sending and receiving systems can understand. We will cover formats like JSON. Data processing involves several steps: validation, cleaning, transforming, and finally loading the data. Python is particularly handy for data manipulation. Next, response handling and exception handling. Handling responses and exceptions is about managing what happens when things do not go as planned. We need to respond to the requester with a corresponding acknowledgement message and automate notifications. Next, data storage. Finally, data storage is about where and how you keep the data. This involves connecting to the appropriate systems, such as a case management system or a database. Now, let's cover how GP offices electronically send patient referrals to specialists or hospitals using REST API, specifically through the use of the POST method. REST is a protocol that allows computers to communicate over the internet using HTTP, the technology behind web browsing. When a general practitioner or a GP needs to refer a patient to a specialist, the computer system will utilize a REST API to send this information. The process is similar to submitting an online form. The GP system makes a POST request, effectively sending a detailed electronic form to the specialist systems. This method is not only straightforward, but also ensures that the referral is transmitted securely and promptly. Now, on to security, which is crucial in this system. We utilize digital certificates to safeguard the sensitive health information being transmitted. These certificates act as a digital proof of identity for both the sending and the receiving system, ensuring that the information is exchanged between authorized entities. This verification is key to preventing data breaches and unauthorized access. Additionally, encrypting the data during the transmission is vital. Encryption converts the readable data into a secure format that only the recipient can decrypt and read. This means that even if the data were intercepted, it would remain unreadable and secure from misuse. By using REST API, with these security measures, healthcare systems can communicate efficiently, ensuring that referrals are processed swiftly and securely. This enhances both the speed and the reliability of patient care. We will next delve into the specifics of how data is formatted, including the use of JSON, to further understand the data handling in this system. Now, let's delve into the data exchange format used in these communications. In this example here on the right, the referral data is formatted in JSON according to the FHIR standards. FHIR, or Fast Healthcare Interoperability Resource, is a standard designed to enable healthcare information to be available, discoverable, and understandable. Its main format for data exchange is JSON. This choice is due to JSON's user-friendliness and its ability to structure complex healthcare data in a clear, text-based format that is both easy to understand and simple to understand. In this example, we have structured patient information, including the name and identifiers that are crucial for unambiguous identification and processing. The resource type field specifies that the data pertains to a patient, which helps the system quickly understand and categorize the information. FHIR's adaptability to handle complex data structures, including arrays and nested objects, allows for a comprehensive representation of patients' history, diagnostic codes, treatment plans, and more, all within the same streamlined document. This maximizes the efficiency of data sharing and integration across various healthcare systems. By utilizing JSONs formatted according to the FHIR standards in our data exchange, we ensure that the information transferred is not only secure but also highly structured to enhance clarity and operational efficiency. This leads to quicker, more accurate handling of referrals and ultimately better patient care. In the next part of our discussion, we will explore how this data is processed and the steps taken to ensure its integrity throughout the referral pathway. Now, let's delve into how this data is processed and the crucial role of managing exceptions and errors during the referral process. When a referral arrives, the first step is to validate the data to ensure it conforms to the FHIR specification and includes all the necessary information. For instance, this includes checking that mandatory fields like patient ID and medical details are present and correctly formatted. Let's consider a scenario where an error occurs during this validation process. Suppose our system receives a referral with an incorrectly filled out gender of the patient, which is given as a W, which is a not recognized code. Here, in our system, here's how our system would handle this using the FHIR Operation Outcome resource. In this example, the Operation Outcome resource explicitly details the nature of the error. It identifies the field with the issue, provides a diagnostic message, and it even specifies where in the data processing code the error was detected. This level of detail is invaluable for quickly addressing errors, ensuring that they are corrected in a timely manner to prevent impact on patient care. Effective error handling like this is essential. When an error is detected, our system logs the details, informs the appropriate personnel, and where possible, attempts automated correction or requests additional information to rectify the issue. By incorporating robust error handling mechanisms and using structured feedback like the FHIR Operation Outcome, we ensure that our healthcare referral system is not only efficient but also resilient. These practices help minimize disruption and maintain high standards of patient care. In our next segment, we'll explore how this processed data is securely stored and retrieved, completing our comprehensive overview of the data lifecycle in a healthcare referral. Now, let's focus on the critical stage of data storage. After referrals are processed using FHIR standards, ensuring secure, compliant, and efficient storage is essential. The initial step in the storage process involves mapping and extracting the necessary data. This means taking the structured data from the referral and ensuring that each piece of the information is correctly placed in the corresponding field within the electronic medical record or a case management system used by the specialist or hospital. Here's how it typically works. Data is received in the FHIR format needs to be accurately mapped to the specific fields in an EMR or other healthcare system. This process is crucial because it ensures that all relevant data, such as the patient details, diagnostic codes, treatment information are systematically organized and easy to access by the healthcare providers. There are different techniques to store this mapped data. Many healthcare systems provide APIs that allow for systematic access for incoming data into their systems. This method is inefficient and minimizes errors as data flows directly from the source to the correct fields in an EMR. In some cases, data might be written directly into secure database tables. This approach is often used when systems that need high level of security and control over the data processes. Ensuring data privacy and compliance with Australian data privacy laws is paramount. These laws dictate how personal information must be handled, safeguarded, and throughout its life cycle, from collection and storage to access and dissemination. We implement measures such as data encryption before storage and comprehensive access controls that meet stringent standards. As data is shared amongst healthcare providers, the potential for breaches increases. It's essential that all sharing protocols comply with privacy laws and that only the necessary information is shared. Each piece of personally identifiable information, or PII, must be handled with utmost care to avoid unauthorized access and use. Our protocols are designed to securely manage and limit exposure of PII, reinforcing the security framework around sensitive patient data. Before capturing any PII, it is crucial to ensure we have the legal authority to do. This involves obtaining consent where required and being transparent about the use of the data. Adhering to the principles not only complies with legal standards, but also builds trust with patients, ensuring they feel secure about how their information is used. To further protect data, PII and other sensitive information are encrypted and stored in multiple locations. This redundancy ensures data availability and recovery capabilities and essential for maintaining continuous patient care. By effectively mapping, extracting, and storing data using these techniques, healthcare providers can ensure that their systems not only comply with legal standards, but are also equipped to provide efficient and timely care. This methodological approach enhances the overall functionality of the healthcare system, ensuring that crucial data is available when and where it is needed the most. Let me take you through a sample referral, and we will send this via an API. Let me take you through a sample referral. On your right, I have a snapshot of what a referral looks like when using FHIR. We can see the actual data structure behind this referral. This snippet of data payload is formatted in the JSON format. FHIR is a global standard that defines a set of rules and specifications for exchanging electronic healthcare data. In this referral, the resource type is a service request. A service request is a resource in the FHIR specification used to record and communicate a request for a service to be performed. This could be a diagnostic procedure, a therapeutic service, or even a referral to a specialist. It captures details such as who this service is for, the reason for the service, when a service is desired, who is requesting the service, and who should perform. The resource can be incredibly detailed, including information such as the location where the service should take place, any specimen that needs to be collected, and any additional clinical information needed for the service to be performed properly. Below the identifiers, you'll notice the status, intent, priority fields indicating the current state of the referral, the purpose of the request, and how urgently it needs to be addressed respectively. Further down, we have a code detailing the nature of the service requested using a system of codes. As we navigate through this sample referral, you'll notice that code and its accompanying coding system, the actual code, and the display values are a recurring trio. This consistent structure across the FHIR format is what allows for precise identification of medical concepts and services. Let's break down to what each of these elements represent. The coding system is a reference to a standardized set of codes such as SNOMED CT, which is used globally to avoid any ambiguity in medical communication. Within this, the code itself is a unique identifier for specific health condition, treatment, or service, a numerical shorthand, if you will. Accompanying this code is a display, providing a human-readable form of the code, which gives us a clear and concise description. And then there is text, a narrative version of what the code represents. It offers a more descriptive and easily comprehensible name for the service that is being referenced, ensuring that the information is accessible to everyone, from healthcare professionals to patients. In this referral example, we use a service request with a code of 306206005 isn't just a number. It's a precise identifier used when a coding system known as SNOMED CT. SNOMED CT, or SNOMED clinical terms, is a systematically organized computer processable collection of medical terms providing codes, terms, synonyms, and definitions used in clinical documentation and reporting. This particular code is used to specify the type of service being requested. In this case, a referral to service system field within our JSON snippet tells us the code comes from SNOMED CT. The display value associated with this code is referral to service. It's a human-readable label that gives anyone reading the data a clear understanding of what the code represents without needing a decipher to the numerical code itself. Now, SNOMED CT is just one example of a coding system. The beauty of using an internationally recognized standard like SNOMED CT is that it promotes consistency and clarity across different healthcare systems and borders, allowing for accurate communication and analysis. These systems can be specific to any organization or government department or national or global standard. While many coding systems exist and are in use, the goal is always the same: to achieve a common, uniform language in healthcare that supports efficient and precise information exchange. Whether we're dealing with a local, national, or international system, these codes ensure that when we say 306206005, a healthcare professional anywhere understands what we're talking about is a referral to service, and this common understanding is the heart of effective healthcare delivery.
Under the identifiers, let's look at the resource type called patient. This segment of the code relates to patient information. You will find a detailed breakdown of various attributes of the patient, including the carer of the patient. As we scroll down our sample payload, let's look at the resource type organization. This is where you'll find information related to the organization or the GP practice who is sending us the referral. In Australia, each of the GP clinic has their own organisational identifier or HPIO. Scrolling down further, let's look at this resource type called practitioner. This segment of the code represents the practitioner information. You'll find a detailed breakdown of various attributes of practitioner or the GP in this case, including the name and their HPI government identifier.
In order to access the API, you will need a tool like Postman or Thunderclient. Let me open up Postman. To access this URL, you will need the endpoints as well as the API key. The API key is a security feature to ensure this API is available only to those with a key. There are other security features we will need to consider, which is outside the scope of this demo. I will also use the post method. For the copy of the payload, please look at the sample provided in the LMS. Before I send the referral, I'm going to first show you the database. In this demo, I have created a Postgres database in Vercel. Behind the scenes, this API will ingest the data, parse the data, and inject it into a table called inbound referral. For now, I have deleted all the records from the database table so that we can see what this looks like after we send the referral. I have gone ahead and created a post request with the URL and the key. You can do the same. You need to click on the body, click on raw, and then copy and paste the sample payload. Let's take a brief look at the FHIR sample payload. And then we'll click on send. If it all goes well, I should expect a response of 202 indicating a success and an operational outcome message also in the FHIR format. I have gone ahead and created a post request with the URL and the key. You can do the same. You need to click on the body, click on raw, and then copy and paste the sample payload. Let's take a brief look at. You can also check out the details of the operations outcome message on HL7 FHIR site, and I've provided the link in the description below. Let's go back to my Postgres database. To verify the API has worked, you can now see a record being inserted into the inbound referral table. Let's go ahead and create your very own referral API. Similar to the previous API I helped you build using a simple JSON payload, this time let's deploy a more sophisticated AWS Lambda function that processes the FHIR payload and responds using FHIR. To create your referral API, the first thing you need to do is reuse your current Postgres database you've created either on Vercel or AWS. You'll need to first create a table called inbound referrals based on the SQL command in the LMS. Next, you must create the Lambda function that handles the referral. I have provided the code and deployed this already on S3 bucket. All you have to do is deploy this using the zip deployment using the link to the S3 provided in the LMS. Next, you will need to create an API trigger using API Gateway. Then we will test this using Postman with a sample FHIR payload I've provided in the LMS. Now, let me show you through the steps, step by step. In AWS Lambda, let's create a function. Let me call it the eReferral FHIR service. Select the Python 3.12, keep the defaults, and let's create function. Now let's go ahead and add the Postgres library as a layer. Add a layer. Click on custom layer, select the Postgres library we had created before, and click on add. Now we'll be replacing the default code. So we'll click on upload from. We'll use the zip deployment. So click on Amazon S3 location. Copy the S3 bucket URL from the LMS. Click on save. Now you should be able to see my complete code. Notice that I have all the environment variables required to connect to the database. So let's go ahead and set up our environment variables. So click on configuration, then click on the environment variables. Now we will go ahead and add all the environment variables from the database. Replace these environment variables using your own Postgres credentials. Click on configure our test. Give it a name. And now let's copy and paste the event from the LMS and paste it here. And now let's click on save. Let's click on test. Great, we can see the successful 202 together with the appropriate response. Now let's create a API. Click on add trigger. Select API Gateway. Create a new API. We'll use HTTP API. Let's keep it open for now. We'll just use the standard defaults for now. Click on add. Alright, now let's go into the API Gateway. Copy this URL, the API endpoint. We will now go and use this in Postman. So let's go to Postman. So let's create a new API request. Click on New, HTTP. We'll set this as a post request. Let's copy and paste the URL from the API Gateway. Click on Body. Click on Raw. Set this as JSON default, so that's great. Let's copy over and paste the sample FHIR payload. Let's click on Send. Great, we've got a 202. This means that our APIs are working correctly. Now, try this on your own. With this video demonstration, I hope by now you have a better understanding of how data pipelines can be established using industry-based standards such as exchange formats like FHIR and coding standards such as SNOMED CT and established communication and transport protocol such as REST APIs, HTTP methods such as POST, security mechanism such as API keys or security tokens, and using tools such as Postman or Thunderclient.